have your parent function. What does the minus 2 do to the graph? And what does the multiplying by 2? Okay, so we have two things to do here. So if I take a point, 0, 0, move it to the right 2, I'm here. Stretch by 2, so just take your y value times 2, and that's still 0. Okay, if you had 1, 1, move it to the right 2. Its y value is 1 times 2, make that 2. If I take 2, 2, and move it to the right 2, it's at 2, 4. It's y times 2, and that takes it up to 4. Negative 1, 1, move it to the right 2, so that's 1, 1. Multiply the y by 2, so it's 1, 2. I'm doing more points than we need to, but I just want to make sure you guys understand how I'm getting it. So if I take 2, 2, right 2, y value is 2 times 2, so we get a skinnier graph that's been shifted over. So my lines aren't super straight, but is that okay? Alright. We're probably going to skip around a little bit. We may not do all of them, but I want to do several that have multiple transformations going on. So if I look at this one, the parent function would be what? Square root of x. So get some exact points. Square root of 0 is 0. Square root of 1 is 1. 4, 2, 9, 3. Okay, so tell me all the transformations here. Vertical compression, shrink. Okay. When you have these, say the up and down for the final thing. Okay, it doesn't really matter if I move left or right or do my compression first, but up and down should be last. So if I take this, it's a y value of 0. So when I multiply that one by a half, it's still 0. Then if I move that left 2, down 3. Okay, 1, 1. If I take my y times a half, it's now at 1, 1 half. We go left 2, down 3. 4, 2. Take my y times a half, now it's 4, 1. Left 2, down 3. Give you one more if you wanted. 9, 3. So if you take your y times a half, left 2, down 3. Our graph looks more like that. Let's do this one. You guys think you could try it? Okay. Try that one first. Tell me what the transformations are. Good. What has to be the last thing we do? Up and down. Okay, so if I take 0, 0 and flip it, it doesn't go anywhere. Right 2 and up 1. If I take 1, 1 and flip it, it goes down to negative 1. Right 2 and up 1. I did 8 or 2, 8 just for practice, so that would take it to 2, negative 8 when I flip. Right 2 up 1. and then do the others. Minimum of 2 points, but you can, or minimum of 3 points, but you can always do more. So graph looks like that. Are we okay with those? All right, let's go to this problem. This is kind of a favorite type of question on the ACT. They give you graphs that look nothing like any of our common functions, just to test your transformations. It kind of prevents you from just being able to plug it in your graphing calculator and looking at the graph, because you don't know what the original equation is. So it really tests if you know your transformations or not. Here's our parent function. I want to graph f of x minus 2. So what would that do to my graph? It's on the outside, a 2 on the end. So we're really just going to find some nice points on this graph, and we'll shift each of those down 2. What about B? So take each of your points to the right. What would this do? So left and up. And final one. All right. So we flip over the x, right, 2, and very last thing has to be the f3. So if I flip 0, 0, it doesn't go anywhere. Right 2, up 3. If I flip negative 2, 2, goes down to negative 2, negative 2. Right 2, 3. Alright, this one is at 1 and about negative 2.5. So we'll go up to positive 2.5. Right 2, up 3. So slightly off my graph there. And 3, 2. Right. So we have kind of an upside down version of the same thing. So we can handle questions like that? So I'm going to move on from transformations now. I think you guys have this. The final thing that I want to look at today is symmetry. Do you remember if we've talked about symmetry at all before? Probably not, but maybe. So you've talked about lines of symmetry probably in an art class or something. Where can you fold your picture so it overlaps itself? We can have symmetry within our graphs. So we can look at graphs being symmetric to the x-axis, y-axis, or origin. So what this says, if a graph is symmetric to the y-axis, f of x equals f of negative x. So it might mean I have some sort of graph. And when I have an x value, this is what my graph looks like. And it's saying that's equal to the exact same thing when my x's are negative. So my y values are the same even when the x is negative. So what it's giving me is a mirror image over here. The y value is the same whether x is positive or negative. If you think about that, if you fold this graph on the y-axis, do those two pieces overlap itself? If I were a better artist, the answer would be yes. Okay, so positive and negative x give us the exact same y value. That's symmetric to the y. Symmetric to the x-axis says f of y equals f of negative y. So we're used to seeing f of x, function notation. F of y, that's referring to the x value we get out when we plug in a specific y. So if I put in some y value, and I'm getting these x's, it's saying when my y is negative, I get the exact same x's. Okay, so if you fold this line on the x-axis, it overlaps itself. So a positive and negative y value correspond to the same x. Is that one a function? No, fails the vertical line test. All right, symmetric to the origin. So, let's say I had some graph. And it had the points 0, 0, 1, 1, and 3, 2. It's saying when the x is negative, the y has to also be negative. So this was the point 1, 1, that would become negative 1, negative 1. This is the point 3, 2, becomes negative 3, negative 2. And this is a graph that's symmetric to the origin. Okay, in order to look at this, you basically have to think two folds. If I first fold this thing over the y-axis, and then I fold it over the x, would it overlap? So it requires a flip and another flip before it will overlap itself. That is a graph that's symmetric to the origin. So three kinds of symmetry. Symmetric to the y-axis, x and negative x give us the same thing. Symmetric to the x-axis, y and negative y give us the same thing. Symmetric to the origin, you have to change the x and the y to get the same thing back. So we can tell symmetry a few different ways. A lot of times we can kind of look at the graph itself and tell, but that's not super precise because they look about the same, but you can't tell if it's exactly the same all the time. So algebraically, what we're going to do is plug in those negatives and see if we get the same thing. So if I want to check if it's symmetric to the x-axis, if it's symmetric to the x, that means whether my y is positive or negative, x is the same, right? So what we're going to do is replace y with negative y. If we get the same equation back, it was symmetric. If our equation changes, it's not symmetric. Okay, so if I put this in, what's the absolute value of a negative y? Yeah, it's same as the absolute value of positive y. So I plug this in. Is that what I started with? Yes. So this means this graph is symmetric to the x-axis. It's possible to have more than one, so we can't just say, oh, we found the symmetry, we're done. So to check the y-axis, you change x to negative x, because if it's symmetric to the y, both whether your x is positive or negative, you're getting the same y value. If I put in a negative x in place of my x, is there anything I can do to turn this back into the original equation? No. So I can't make this the same. So this is not symmetric to the y-axis. To check origin, you do both. Y becomes negative y, x becomes negative x. So if I do that, I have negative x equals the absolute value of negative y. So I get negative x equals the absolute value of y. Is that what I started with? No. So this graph is symmetric to the x-axis only. If you looked at a graph, we'd have to plot it by hand, but it's like a sideways absolute value. So we could see it's got that symmetry to the x-axis. All right, let's get B. How do I check the x-axis? So if I make my y negative, is there anything I can do to get rid of that negative and turn it back into the original? No. So it's not symmetric to the x-axis. To check the y, replace your x with a negative. A negative cubed is still negative. Negative 2 times negative x is positive 2x. Is that what I started with? No. And there's really no way to get it. To check origin, we do both. So if I make my y negative and make my x negative, is there anything I can do to turn this into the original? Yes. I could divide by negative 1 on both sides, and that gives me a positive y equals positive x cubed minus 2x. Is that what we started with? Yep. So this one is symmetric to the y, or to the origin only. Okay. So far, so good? Why don't you guys take a second and check the next one? So check x-axis, you make your y negative, that gives you 2x plus y equals 6, which is not the original, so it's a no. Y-axis, make x negative, you get negative 2x minus y equals 6, so that's a no. Origin, you get negative 2x plus y equals 6, and that's still a no. So it's possible to have a graph with no symmetry at all. In this one, it didn't matter what we did. Last one, if I make my y negative, what happens when you square negative? And is that what we started with? Yes. Okay, for the y-axis, if I make my x negative, that becomes a positive x squared plus y squared equals 25. Which is what I started with. Origin, if I do both, also get what we started with. So with symmetry, it is essential to check all of them because you could have everything be a yes, you could have everything be a no, or you might have one yes in the whole list. So we can't just say, oh, I got a yes, I'm done. You need to go ahead and check them all. Is that okay?
I have a question.
Yes.
On like the letter D, like you put the square back on it.
Yes.
Why don't you just like drop it?
So when you have, for instance, negative x squared, that means you have a negative x times a negative x. So a negative times a negative made a positive. X times x made it x squared.
And then you just don't, you just leave the square on.
Because we don't know what x is to get turned into a number. So really all we're squaring there is the negative piece in the variable. We just leave it. Other questions? So we've already kind of touched on with these symmetries, we know that symmetric to the x-axis is not a function, but the others are. So with functions, a lot of times you'll hear the terms even and odd, and that's just asking about symmetry. Even means symmetric to the y-axis. Odd means symmetric to the origin. I kind of remember it by the O's go together. Odd is origin, so even is the y-axis. So if I asked you to decide if these functions were even, odd, or neither, I'm basically asking you your symmetry. If I look at this one, what's it symmetric to? The y-axis. And symmetric to the y-axis means even. This one, is it symmetric to the y-axis? No. We know it's not symmetric to the x-axis because it wouldn't be a function. Symmetric to the origin, so you have to think, okay, if I flip this over the y and then flip that over the x, would it overlap what I started with? Yes. So that's what we call an odd function. This one. So if I think symmetric to the y, I'd have to flip over the y and overlap, and it doesn't. To check origin, we're thinking, okay, if I flipped it over the y, what's it going to look like? And then if I flip that over the x, does it overlap itself? Yes. So this one's also odd. What's this one? Odd as well. It takes two flips before it overlaps itself. All right. So I might give you something in function notation, and instead of saying find the symmetry, I might ask you if it's even or odd. And there's really two approaches for doing that. Instead of f of x, we could change it to a y, and then we can do it like before. We know even is symmetric to the y-axis, so that means you plug in a negative for your x. Odd is symmetric to the origin, so you make them both negative. The other option, in function notation, it's a little bit easier. If it's even, symmetric to the y, that means whether you put in a positive or a negative x, you get the exact same thing out. So if f of x is equal to the same thing as f of negative x, positive and negative x giving the same thing, then that's considered even. Odd tells me if I put in a negative, if x is negative, it makes y negative. So you get the opposite of what you put in. So we could do it like before, or we could find f of negative x. So if I put in a negative, if you square a negative, it becomes positive negative x times negative x. It's just x squared minus 5. This is what I started with. That means f of x is equal to f of negative x, which means my function is even. A positive and negative x give me the exact same answer. On b, if I put in a negative for my x, a negative to the third is still negative. Is that what I started with? No. Okay, so even says whether x is positive or negative, we have to get the same thing, so we know it's not even. Odd says if x is negative, y is negative. Is this the exact opposite of what I started with? That means, is it the same as taking the original times negative 1? No, so this would be a neither. Yeah. So negative to the third would still be negative, so we get negative 5x cubed minus a negative, so that's plus x. Is that what I started with? No. Is it the exact opposite? Yes, so that is the definition of odd. So if it's written in function notation, it's actually a lot easier, so we can just plug in our negatives. Okay, is this okay with everybody? So you have the next few minutes to finish that handout from yesterday, due tomorrow.